continue with the gradient vector. So last time, the last section we talk about the directional derivative is actually equal to the partial derivative with respect to x times a plus the partial derivative with respect to y times b, where a and b are components of this direction vector, the unit vector. Okay, now this is the theme that we just talked about, theme 3. Looking at this, well, this times this plus this times this, that we might as the dot product, right? So remember when you take this vector dotted with this vector a comma b, that's exactly the same result that you got over here. So we can think about this directional derivative of the function in the direction of u as the partial derivative with respect to x, partial derivative with respect to y, this vector over here dotted with the vector u. So that is actually an easy way to remember, isn't it? So you take a vector that has the x component to be the partial derivative with respect to x, and then the y component will be the partial derivative with respect to y, and then you dot it with the vector u, this unit vector u, that will be the directional derivative of the function in the direction of u. Remember, u here has to be a unit vector, okay? So that actually is an easier way to remember, okay? Think about it as a dot product of this. Now, because this vector over here, this vector over here occurs not only in computing directional derivative, but in many other contexts as well. So we're going to give a special name. The name for this is called gradient, the gradient of f. Okay. So you can denote it as GRAD, okay, it's for gradient, or you denote it with this upside down triangle, which is read as del f. Okay, so we call it del f. The gradient here basically is you take the partial derivative, okay, with respect to x, okay, and then the partial derivative with respect to y. Those are the components. Okay, so here is the definition for gradient. Okay, so it looks a lot simple, but keep that simple and think about that. The gradient, the component of the gradient is just a partial derivative in the x direction and in the y direction, etc. Okay, so that's the definition for the gradient. Okay, partial derivative. Question? It's gradient. I haven't looked up the Chinese for this. Well, let's try to do some example to understand gradient a little bit better. Okay, so we're given this function here. Let's compute the gradient of the function. You can also call that del f. Okay, del f. So what would that be? Anyone? All right. So what's the first component? The first component will be, remember the component of the gradient, those are just partial derivative. So the first component will be partial derivative with respect to what? X. And then second component partial derivative with respect to y. So all you have to do is just compute the partial derivative, right? Okay. So let's do that on the side. Let's compute the partial derivative with respect to x. And the function we have over here is sin x plus e to the xy. Remember when you compute partial derivative with respect to x, you think about the other variable as fixed, right? So partial derivative with respect to x, so we're going to fix the y. Think of y here as fixed. Think about that just like a constant, okay? And we focus on the variable. And the variable over here is x. So those x here is the only changing variable. So what is the partial derivative of this function with respect to x? The derivative of sin x with respect to x is what? Cosine x and then plus, okay, now get to this one. What's the duality of this with respect to x? Yes, you got it. Okay. Now e to this function, okay, it's a composite of function. We need to use a chain rule. The outer function is e to the u, right? We got this as a single variable, e to u. So that will be e to the x times y itself. And then use the chain rule. We multiply this by the duality of this inner function, x times y. The duality of this function with respect to x is just y, so times y. So Melanie, you got this right? Okay, good job. Okay. So that's how we got this partial duality with respect to x. Okay. Now, can you write down the partial duality with respect to y? What is this? What's the duality of this with respect to y? 0. And what's the duality of this with respect to y? X times e to the xy, right? You got it. Good. Okay, so we got that. Okay, good. So yeah, now you just compute the first gradient in your life, okay? You did it, okay? Not that complicated once you think about this way, right? The component will consist of partial duality, okay? Okay, now we will find the gradient of this function at 0, 1. And all we have to do is what? Substitute x to be 0, y to be 1 into these two components, right? Okay, so substituting, okay, so we're going to plug it in. And now, can you guys do the computation? So x equal to 0, y equal to 1. What will be the first component? What does it equal to? 2? Yeah, you got it. Good job. Okay. And then the second component will be 0. Yes, you got it. Good. Very nice. So you have compute gradient, okay, successfully. So that you did a good job. Okay. So it's not that scary once you did some example, right? Okay. So we will use the notation. Okay. So this, remember the directional duality in the direction of u is this dotted with u, right? Now this one over here is the gradient vector, right? This is a gradient vector. So we can rewrite this as the gradient of the function dotted with u. So if you try to find the directional duality of the function in the direction of u, you just take the gradient and dot it with u. So that's it, okay? Let me color code this. This u here is a unit vector, okay? That's the unit vector u. So to compute the directional duality with respect to directional duality in the direction of u, you just take the gradient dotted with u. When you dotted that, right? Dotted that is the scalar projection of the gradient. Remember, how do you perform dot product? When you dotted them, like a dot b is equal to this, right? It's the magnitude a times magnitude b times cosine theta. So basically is how long is the shadow, right? Actually, this is the length of the shadow of this A, okay? Well, actually, it's the magnitude A is the B times the magnitude of A times cosine theta. This part over here, A times cosine theta, is the shadow of this A. Is the magnitude of the shadow of this A, right? So looking at this, when you dotted this, that is the scalar projection of this gradient vector onto the U. Okay, now we get to functions of 3 variables. Well, it's very similar to function of 2 variable. When function had 2 variable, we didn't have this part here. Now, the directional duality of the function of 3 variable at x naught, y naught, z naught. Last time we have these 2 components, right? Now we just need to add one more component. So we have z naught plus hc. Remember this direction vector ABC, right? Has three components, ABC, okay? And you just put ABC here. So you just add one more component for the definition, okay? That's it. So similar as before. And similarly with other, okay? So you can actually combine the definition for directional duality for functional two variable or three variable, or maybe even more variable using this definition. So this is the x naught vector plus hu. Remember the u here is the direction vector. Okay, the u here is the direction vector. And this u over here, this is hu. Okay. So it's the vector x naught plus a scalar multiple of the direction vector, subtracting this. Now this one here looks very similar to the definition for duality, right? Okay, so that's the one. So this is going to apply when function is a function of two variable or three variable or even more variable. Now what about the gradient? Now last time for function of two variable, then the gradient has two components. The first component is the partial derivative with respect to x. Second component is the partial derivative with respect to y. Now we just need to add one more component. So that's the partial derivative with respect to z. That is the gradient vector when the function is a function of three variables. So just add one more component. Okay. And maybe this one here is easy for you to remember. Fx, Fy, Fz. Okay. This vector here is a gradient vector. And if you put the IJK expression, that looks like this. Okay. So again, so the directional duality of the function in the direction of u is a gradient vector dotted with the direction vector. Okay, so let me put it out for you. So the u here is the direction vector. So that gives you the direction. Okay, and what is this part over here? This one over here is the gradient vector. And what is this one over here on the left side? This one here on the left side over here, let me choose a different color. This one over here is the directional duality. So this formula says that directional duality is a gradient vector. Oh, I misspelled this. Okay. It's a gradient vector dotted with the direction vector. And this is the dot product. So that's the important formula to remember. Okay, let's try some example so that we can understand this better. So it's actually, if you know how to take duality, then it's actually not too bad, okay? Now we're given this function. This is a function of three variables, x, y, z. Part A, we try to find the gradient of the function. Okay, let's find the gradient of function. So let's find out the component. So what are the components of the gradient vector? The first component will be what? Partial derivative with respect to x, and then partial derivative. The second component, partial derivative with respect to y, and then the last component, partial derivative with respect to z, right? Okay, can you guys find the partial derivative of the function with respect to x here? What is it? So let's focus, think about x as the changing variable. The sin of yz here is going to be a constant, right? So when you have a constant times x, when you differentiate with respect to x, what do you get here? Sin of yz, right? I hear you. So sin of yz, okay. Okay, good job. Okay, now the next one, partial derivative with respect to, this time is with respect to y. So think about the y here as the only variable. x and z are constant. Differentiate this with respect to y. What do you get? Well, let's try this out, okay? So the x over here, think about is the constant multiple. So certainly we'll just copy, right? And now what's the derivative of sine of yz? Yeah, the outer function is sine. So the derivative of sine is cosine. So let's write down cosine. And whatever inside, you just copy, okay? The inner function keep it unchanged. Now multiply by the derivative, this inner function, what's the derivative yz with respect to what? Z. Okay, so you get z right here. So this will be partial derivative of the function with respect to y. Okay, so I'm going to put it over here. Okay, now can you guys find the partial derivative of the function with respect to z? Looks like the y and z are kind of symmetry, right? It has a symmetric, right? So from here, you're looking at the second one, you know the last one. What is it? Very good. Okay, thank you. Okay, so xy cosine yz. Okay, good job. Okay, now we just compute the gradient. Now the second part here, part B, we try to find the directional derivative of the function at this point. So all we have to do is to substitute, right? So I'm going to substitute x to be 1, y to be 3, and z to be 0, and into this expression, okay? Can everyone tell me what do I get? Substitute, well, remember the z equal to 0. When z equal to 0, this is sine of 0. What's sine of 0? 0. Okay, good. Okay, get the next one. Next one here is, well, when z equal to 0, what happened to this? 0 times anything is 0, right? So the second one is also 0. Okay, the last one. 3. Yeah, you got it. Good job. Okay. So cosine of 0 is 1, and then you have 1 times 3. So it is 3. Okay, good. Now, remember, this is not the u yet. This is the gradient. What is this, right? This one here is a gradient vector, okay? This is the gradient vector. Okay, that's a gradient vector. So we compute that. Now we're trying to find the unit vector, right? The unit vector in this direction, right? This u over here. Okay. Okay. The second part is trying to find the directional derivative of the function in this direction. Okay, this one here is not u. Okay, this is not u. It's not the unit vector. This one here has to be unit vector. Remember, we find directional derivative. What was the formula to find directional derivative? We take the gradient and dot it with what? Dot it with u, right? Okay, now we found the gradient already. We just need to find the u and use the gradient dotted with u, okay? But then this one here give you the direction, but that's not the unit vector. How can I make this a unit vector? Divide by its magnitude, okay? So we have this. What's the magnitude of this? Do the calculation. Square root, right? Square root of 6, okay? So its magnitude is going to be the absolute value. The magnitude of this is equal to square root of 1 square plus 2 square plus negative 1 square, which is square root of 6. So this is the magnitude of this vector. We're going to take this one and divide by the magnitude. Then we're going to get 1 divided by square root of 6 in the I direction, 2 divided by square root of 6 in the J direction, negative 1 divided by square root of 6 in the K direction. And now, is this a unit vector now? Yeah, it is, right? Okay. Now, if we try to find, okay, remember, keep in mind, what are we looking for? We're looking for this directional derivative, right? So the directional duality, what was the formula? It is the dot product of the gradient. Too much. Okay, it's the dot product of the gradient with the direction vector, right? So this U right here. Okay, so we just take the dot product. Okay, good. So this is the dot product. Okay, the gradient. Okay, the gradient is this one. Okay, that's the gradient vector. Okay, and this is the U right here. If I write it this way, okay, let's write it this way. So 0, 0, 3 dotted with the other one is what? 1 square root of 6, 2 over square root of 6, make it 1 over square root of 6, okay? Do the calculation, okay? What do you get? This first two component will become 0, right? What's 3 times this? 3 times this is what? So you get 3 times negative 1 over square root of 6, which is negative 3 over square root of 6. I think they would take this, okay? They would take this, but if you, there are different way to write this. You can either rationalize this, you can also put it like negative 3 over 6 and then square root of 6 and then reduce this to this, right? Okay, but in any case, okay, you got this number, the equivalent, okay? Okay, good. Well, congratulations. And you just calculate this gradient and also directional duality for function of 3 variables. Okay, you did it. The second topic here will be maximize the directional duality. How do we maximize this? This actually has application. Okay, a lot of time you want to find, you want the directional duality to be the maximum. Okay, so it's how can I make the rate of change the biggest? Okay, I forgot to start with the application, but any case, you can look it up. Okay, so suppose we have a function of 2 or 3 variables and we consider all possible directional duality at a given point, and that will give the rate of change in all possible direction, right? So if you change the direction, then the rate of change of z is going to change, okay? And then you're going to ask yourself, okay, which direction gives you the maximum rate of change, okay? And the answer for that is providing by this theorem over here. Okay, what does this one say? So suppose the function is differentiable function of 2 or 3 variables. The maximum value of this directional duality is the absolute value of the gradient. So basically, it's just the magnitude of the gradient. Okay, and when does it occur? It occurs when the direction vector u has the same direction as the gradient vector. So if you point the direction in the direction of the gradient, then the rate of change will be the fastest, the greatest, okay? Now, I give some reasoning here, down here, okay? So remember, so what's the reasoning, okay? So directional duality of the function in the direction of u, okay? I always feel that color coding this make it easier, okay? In the direction of u is the dot product of the gradient vector with u, with the u over here, okay? Remember, it's the dot product. How do we do dot product? Dot product is you take the magnitude of the 2 vector times cosine theta, right? Theta is the angle between them. So here you take the gradient dotted with this direction vector. So you take the magnitude of the gradient times the magnitude of u, and then times cosine of theta, the angle between them. What is the magnitude of u? U is 1 because it's a direction vector. It's a unit direction vector. Remember, we make it unit, right? So the magnitude of that is 1. It's a unit vector. Now, in order to maximize this, we just need to maximize this cosine theta, right? The maximum of cosine theta is 1, right? And when does it happen? When theta equal to what? Cosine theta equal to what? Equal to 0. Yeah, you got it. So when theta equal to 0, cosine theta equal 1, then this dot product here will be maximized. So which means that when theta equal to 0, which means that this direction vector and the gradient vector will be in the same direction. So when they're in the same direction, the directional vector will be maximized. Does it make sense? Okay. All right. So now go back and let's repeat the result one more time. Okay. So the function has the maximum directional duality when the gradient and the direction vector are in the same direction. And what's the maximum directional duality? What's the maximum directional duality? Is equal to what? Equal to the magnitude of what? The gradient. The magnitude of gradient is the maximum for all those directional duality. And it happened when the gradient and the direction go the same way, same direction. And that is the maximum. Okay. All right. So that's a result that is worth remembering. And now over here, I give another review. Sometimes you learn so much, and then you have to say, wow, what did I learn, right? So I give a review here. Again, okay, directional vector, directional duality, okay, is the slope of the tangent, is of the t, okay, at this, and that is the rate of change of z in the direction of u, and that's the definition. And we have the theme. And now I put the theme here in, okay? So this theme here. So directional duality of the function is maximized when the direction is in the same direction as the gradient. And the maximum will be the magnitude of the gradient. Okay, so I put that in. And I also put this one in. Directional duality is the gradient dotted with the direction vector. Okay. And I gave some reason here. And I also, I'm not able to do the animation, but you guys can try it at home. Okay. And over here, I have an example for animation. Okay. Even though I couldn't do the animation, but let's do this example. So I have this function. So the gradient of this is going to be, well, you take the partial derivative function with respect to x and with respect to y. So that will be 2x and that will be y. So that's the gradient. And let's think about at 1, 1. You substitute x to be 1, y to be 1. Then the gradient vector will be 2, 1. I actually should erase this to let you guys figure this out. But anyway, I leave it there. So that's the gradient, right? That's the gradient vector at 0.11. If I try to maximize the directional duality, then I will take the direction in the same direction as the gradient, right? Okay. But this gradient vector, so in the same direction as this. But if I try to figure out the u, the unit vector in the same direction as this, I will need to take this vector and then divide by what? Divide by is magnitude, right? The magnitude of this is square root of 2 square plus 1 square, which is square root of 5. So I take the gradient vector, divide by its magnitude, then I get a unit vector in the same direction as the gradient. These two have the same direction. This is not unit vector, this is a unit vector, okay? Which is about this. And according to the theme, if I make the direction in this direction, then the directional derivative should be maximized, right? According to the theme. Then you can go back and play around with the animation. Okay. Then you would change this. So you change the U here. Whatever number I put over there, you change the U by rotating this arrow over here. You change the U. And when you change U to this number, okay, remember to this number, this vector over here, then you will see that the directional derivative down here is actually the maximum. And if you move away from that U, all those numbers will be less than that. Okay, so you can try to play around that at home. Okay, so you can try the animation. Okay, so in the direction of the gradient, the directional derivative is maximized. Okay, now let's try some example. We're given this function. This is a function of two variables. Find the rate of change of the function at this point in the direction from P to Q. Okay, what does it mean? Okay, take a moment to digest and think about what are they asking? What are they asking? What is the rate of change of this at this point in the direction of this? Okay, in the direction, let me use a different color. In this direction. What direction? So that direction is, well, that will help us to figure out what this direction from P to Q. Okay, from P to Q. Let's figure this out. Okay, so P is, let's write it down. P is 2, 0, right? Okay, Q is 1/2, 2. So the direction from P to Q, this direction. Remember how we calculate this vector, right? We just use this n, subtract this n, right? Okay. So that will be a vector that has two components. So the first component will have 1/2 subtracting 1/2 subtract what? 2, which is going to be negative 3/2, right? And then 2 here subtract 0. The second component will be 2. So this direction is PQ. Is this a unit vector? It's not a unit vector, right? How can I make this a unit vector? So we try to figure out this U, okay? So U is equal to, we're going to take this vector and then divide by what is magnitude. Okay, let me tell you, and you trust me, okay? That is going to be, okay, whatever. So this one over here is going to be this vector. Divide by is magnitude. And it turned out that it's going to be negative, I'm going to use this color here. Negative 3/5 and then 4/5 here. So this is a unit vector in the direction of P to Q. Okay, all right, that's good. Now, what are they looking for? They're trying to find the rate of change of the function at this point in this direction. So basically, they're trying to find directional derivative, right? So okay, let's put it down. So trying to find directional derivative. Okay, let's put a d there of the function. In what direction? In this u direction, right? Okay. So in this direction u, at which point? At this point, 2, 0, right? Okay. So we put 2, 0 over here. So basically, you're looking for the directional derivative of the function in the direction of this u at this point 2, 0. Okay, right. So it's actually very important to understand what are we looking for. Otherwise, we don't have any direction. Okay. So in order to compute this directional derivative, we need, what do we need? We need gradient, right? And we also need the direction vector, right? Okay. You can remember that? Okay. So if I know the gradient and we also have this direction vector, what can we do with them to get the directional derivative? We can take the dot product, right? Okay. So let's compute the gradient vector. Okay. So what's the gradient vector here? Well, let's get the formula. So the gradient vector of the function basically is what? The partial, each component will be the partial derivative function, right? Partial derivative with respect to x, here partial derivative with respect to y. What's the partial derivative this with respect to x? Let's focus on the x. Think about x as the only changing variable. What's the derivative of this with respect to x? E to the y. You got it. Good job. Okay. And what about the partial derivative with respect to y? Any other people? Yeah, so Melanie got this right, okay? So it's x times e to the y, okay? Okay, good job. Now, we need to compute the gradient at 2, 0, okay? Because we're going to use that to dot it with the direction vector, right? So we're going to substitute x to be 2, y to be 0. So put, okay, tell me what do I get here? What's e to the 0? 1, okay, good. Okay, and then the second component, did you say 2? What did you say? Yeah, 2. Okay, good job. Okay. All right. So we found the gradient. Okay. Now we found the gradient and we also find the, well, here, let me just put this in. We find this u. We found the u over here. The unit vector, the direction vector, remember? This is the direction vector. And this one here is the gradient. Okay. At the point 2, 0. Then all we have to do is we can take the dot product of this with this direction vector, right? Agree? Okay. So let's take the dot product. I'm going to take the dot product here. So take the dot product. I will emphasize this is the dot product. Okay. So I'll put a big dot over there. Okay. So that's the dot product of this 2. Let's write down the 2 vector. So the first one is 1, 2. This one here is negative 5 over, negative 3 over 5, and then comma 4 over 5. What's, okay, can you guys do the computation? What does that equal to? Say it louder. Try that. 1? Yeah, it's 1. Okay. So that is 1. Okay. That's equal to 1. Okay. All right. So we got this. We got this. Okay. So this is what does this represent? What is this? How to say that in words? This is the directional derivative, right? So that's the directional derivative of the function f in the direction, in the u direction. Okay, in this u direction over here. Now, according to the theme that we just have, okay, so let's look at the second part of the question. So we finished the first part, part A. We found the rate of change of function at this point in this direction. Part B, in what direction does the function has maximum rate of change? And what is the maximum rate of change? And that we might as about the theme that we talk about. If you want to have the maximum rate of change, the maximum directional derivative, then the direction has to be in what direction? In the direction of what? The gradient, right? We found the gradient, right? That's the gradient at this point. Okay, so if the direction will be in this direction, then the rate of change, the directional derivative will be maximized. Okay. Now this one here is not a unit vector. How can I make this a unit vector? Divide by is magnitude. What's the magnitude of this? Square root of 5, right? So divide by square root of 5. Divide by its magnitude, square root of 5. That will be the vector in the direction of the gradient, which is about this number. Now, for homework, if they ask for exact number, then you will have this. Okay, this is just approximation. So in this direction, so someone said, should I put this one or this one? If they just ask you the direction, then it doesn't matter. Because in this direction, they're the same direction. You can either put this one or this one. Okay, they should both be correct. Okay, so won't be deducted. No point will be deducted. Now, they will also ask, what's the maximum rate of change? Well, what's the maximum rate of change? What's the maximum directional derivative? It is the magnitude of the gradient, right? So we have the gradient over here. We just need to compute its magnitude. Then we know that that is the maximum for the directional derivative, right? So what's the magnitude of this one? We did that already, right? Which is what? Square root of 5. Okay, so that's the square root of 5. Now you can go home and play around with the animation. You can graph this. You can graph the function. Okay, and I tried it myself. Okay, and I've changed the direction in different way by tuning this view, and I found out that if I make the direction in the same direction of the gradient, the directional derivative is maximized. Okay, so you can try that at home. Can I ask someone to read this? Any volunteer?
Now someone employs in which the gradient vector is sitting for them.
Okay, very good.
We first consider a function of 3 variables. Initial x, initial y, initial z, and extending.
Okay, very good. Thank you. All right. How about Isaac? Could you read from here to maybe to here? Gradient vector down, call it down. Yeah.
It's the direction fast. In between. Well, I think the differential is the differential.
Differentiate function. Should that be differentiable? I think it should be called differentiable, but anyway.
Well, I think the differential function, two or three variables, matching value of the directional derivative.
Okay.
The magnitude, the
Gradient vector.
gradient vector. And it occurs when u has the same direction as the gradient vector.
Del of x.
So,
Okay, great. So this actually, well, we have this one before, right? So if you have a function that's the differentiable function of 2 or 3 variables, then the maximum directional derivative is going to occur when the gradient vector and the direction vector are in the same direction, okay? And the maximum will be the magnitude of the gradient vector, okay? So we actually use a picture to demo that, right? Okay, good. Significance. Okay, so that was the first significance. Okay, so it is it gives you the maximum directional derivative. Okay. Okay, number 2, the significance of the gradient vector. Maybe ask, say, who want to read this? Matthew read that one many times. You want to do it again? Okay. Number 2 from here.
on the other hand, delta,
Oh, not delta. Del. DEL.
del
Yeah, del.
f of x0, y0, z0, is
Orthogonal.
orthogonal to the whole surface S of f to the third degree.
Okay, good. Okay, let's stop here, pause a moment, and think about what it means. So the gradient is orthogonal to the level surface. Okay, so look at this. The here is the surface for the graph of the function. Okay, and the level surface over here at this point. Okay, the level surface. The level surface is going to be, oh, this is a function of 3 variables. So think about this blue one here as the level surface, okay? So the blue surface is a level surface at this point, okay? Then the gradient vector is going to orthogonal to the surface. So how do you orthogonal to the surface? So if you have a tangent plane to the surface, so imagine you patch it, right? The tangent plane right there, tangent to the surface at this point, then this vector will be the normal vector of the tangent plane. Okay, so the gradient vector is orthogonal to this level surface. Okay, so it's orthogonal to level surfaces when you have a function of 3 variables. Okay, if you have a function of 2 variables, that will be orthogonal to the level curve. And maybe ask someone else to read this. Weiner, could you, Rainer or Reiner? Rainer, okay. Rainer, could you read from here to here?
These two properties are quite compatible intuitively because as we move away from C on the level surface S, the value of S does not change at all.
Okay.
So it seems reasonable that we move in the perpendicular direction we set in that.
Yes, very good. Good. So this is the level surface, the blue one, right? So as you move along the surface, the function value doesn't change. So it's reasonable to think that if we move in the perpendicular direction to that level surface, it will get the maximum increase. Okay, so that makes sense. Okay, good. All right. Now we go back to function of 2 variables. Okay, so if a function of 2 variables, then the gradient vector, take a look at here. So the green one here is the level curve. And this pink one here is the gradient vector. The gradient vector here is perpendicular to this level curve, which means that if you draw a tangent line of this level curve at this point, this is going to be perpendicular to the tangent line here. Okay, so let me label this. So the pink one here, this is the gradient. This is a gradient vector. Okay, that's a gradient vector. And this one over here is a level curve, and this one over here is a tangent to the level curve. The gradient vector is this way. And if you go along this way, that will give you the direction of the faster increase of function. Because if you go along the level curve, the function values remain the same. So if you go perpendicular to that, that will give you the fastest increase of the function that way. Okay. Now here is a contour map. Okay. It consists of all this level curve over here. This is a topographical map of a hill. Okay. Then a curve of the steepest ascent, you can draw it this way. So start from this and you draw this curve over here that is perpendicular to all those level curve over here. Think about that. You climb the mountain or you go down the mountain. If you go this way, it's actually the steepest. Okay. Imagine you climb the Mount Everest or anything. This is the steepest. Probably not the route that you want to take. Okay. This is the steepest route. Okay. All right. Let me ask someone else to read this. Anybody? How about Darren? Could you read from here to all the way to the end? Okay, very good. So the pink one, those pink line there, those are level curve. So the blue arrow there, they stand for gradient vector. So the gradient vector are perpendicular to those level curve. Okay, you can see. And they point uphill and perpendicular to the level curve right there. Can you see? Can you see how that goes?